bad enough to do. Guys, there's 3 more tests. And let's review the first test. 3 of them are on the board, but let's write them again. The very first thing that you do. Yeah, that is. No, it's just the phone. It just does that. No, it's not. Anyway, it does interfere. Okay, the very first thing you do with infinite series is you test the sequence, A sub n. And if that is not 0, the series diverges. So some of you didn't do that in your homework. Some of you tried to do other tests. That's the very first thing you try. The minute you find it's not 0, you're done. Stop. Okay, then the next thing you look for are the, what? Which one? Geometric. And those, I'm guaranteeing these are on the exam. It's something, it's an exponential function, AR to the n. Right. And some of you took r greater than 1 and found the sum of the infinite series, but it doesn't converge, so it's not equal to that sum. Aaron, can you see? Can you see? Aaron. Yeah. It looked like you can't see. Okay. The next one are those collapsing sums, and really all I need that for is he's squinting. And you can sit closer. That's a collapsing sum. But you know what? It's easier to do that and say, well, this is just n squared minus, guys, n squared minus 1, and see that that's going to look like a piece series. We have to be careful about that one. Oh, yeah. So that's a collapsing sum, and we know that they're going to converge. But generally, I would probably use a p-series test on that instead. So then we added a whole bunch more tests. We added, what was next, remember? The integral test. Because if the integral converges, then the series converges. If the integral diverges, the series diverges. So that was pretty logical. Then we had what? We had before we had the comparison test, we had to have the p-series test. And that's just saying that if you have the summation of 1 over n to the p, it converges for p greater than 1. Know that the integral of 1 over x to the p dx converges for p greater than 1. So now you got to be careful, 1 to infinity. It is not true if you're going from 0 to 1. So you've got to read your limits of integration when you're looking at that. So be very careful, because I've seen students make a mistake on that. Yes, it does. It's a totally different problem. 0 to 1. Okay, so let's see. We had piece, this, oh, and then we had the comparison test. And the comparison test is wonderful, except that it's very hard to show that if a sub n is less than b sub n, that has to be true, and then b sub n has to converge. We also have to have a sub n greater than b sub n and b sub n diverges. If you have any of the other situations where a sub n is bigger than a convergence series, it tells me nothing. Let me draw you the picture. So if you are looking at this integral, and we're going to say it converges, and we're going to say that series converges, that this series is bigger than that. Do you know anything about it? Nope, you don't. So that's the problem. Whereas if this were to diverge, and this is down on this side of it, smaller than that, then you don't know what's happening there. I'm going to ask for the side conversation, so please stop. Because it's just noise in my ear. Okay, so you have to realize it only works in certain cases. It's 1 over n squared minus 1. How does that compare to 1 over n squared? Now, I made the denominator a little smaller, so the fraction gets to be a little bigger. So this is bigger than that. Now, for all practical purposes, well, you know, it looks just like that. The problem is, remember when we had this r to the n? And when we had r equals 1, it was always 1. If we had r bigger than 1, it went off to infinity. And if r was less than 1, we went to 0. So the problem is, if you are at that boundary, if this is the boundary right here, then it does matter which side of it you're on. You might be close enough that it's okay. And these are going to do the same thing. It's okay, but you can prove it with a different test. But if you took 1.000001, that diverges, where you get 0.999999, that converges. So that's the problem. It depends on how close to that boundary you are. If you're on one side or the other, right next to it, then you can't just assume you have to do the next test, which is called a limit comparison test. Remember what that was? The ratio. And I know it's a lot of stuff to know. Trust me, it just get a little bit easier actually when you get into the infinite series themselves, because most of the tests are pretty simple, like a P-series. And you'll see what happens. You just have to wait for a second. But it's the limit as n goes to infinity, and it's a sub n over b sub n. B sub n is the one we know. At least that's been my experience. If I put that in the denominator, it works out nicely. If this is equal to a constant, now, the constant must be greater than 0. So if it's 0, if it's infinity, we don't know anything. So that's a problem. I get that. So you'll try this test and it's going to fail because you get 0. You go, okay, that didn't work. So let's do this problem right here. I think they're both going to do the same thing, but the only way I know is to do a limit comparison test. So it's the limit as n goes to infinity of 1 over n squared minus 1 over 1 over n squared. And if that ratio is a constant, then they both do the same thing. Does that make sense? If you ratio all the terms in this one, and if you ratio them, it ends up being the same, just a constant. It should be the same thing, right? For the most part. So I'm going to multiply by n squared over n squared, and I'm going to get the limit as n goes to infinity of n squared over n squared minus 1. And what's that limit? That's 1. That's a constant. That means they both behave the same. So, since this one converges, the 1 over n squared converges by the limit comparison test. And I'll give you AP questions to practice with. I've got a whole bunch of stuff pulled for you already. And you're going to find out it's not that bad. Most of the time it's going to be geometric or it's going to be something really obvious. It's not going to be something complicated. So if I had this 1 over n times the square root of n, does that converge? Well, that looks like this. It's 1 over n to the what? 3 halves. Does that converge? Yes, because what? 3 halves is greater than 1, so it's the P-series. And that's all you have to write is P-series. So it takes longer to explain this than it does to do. Although in 8.4, when we get to the ratio test, that's not true. But for the most part, that way or the other way? That way. There we go. Okay. Just have to ignore all the mathematics that's written down this. But this is an alternating series test, and it just boils down to 3 things. Okay? First off, this is how we're going to handle some of the negatives. If they alternate in sign, they have to alternate in sign, okay, girls? So that looks like a negative 1 to the n, or n plus 1 power. These are for alternating series, and terms alternate in sign. If they don't alternate in sign, then you can't use this test. So we've seen the alternating harmonic series. You know that one. There it is. Can you write it in sigma? It's negative 1 to the n. Does that work, Logan? Does that work? I need a positive 1, so this has to be what? N plus 1. It should. And then this is 1 over 1, so this is what? 1 over n. That's called an alternating harmonic series. and it does converge. And the theorem says that if they alternate in sign, so that's one thing, you have to alternate. Also, so we have to have alternating in sign. You also have to have the limit of b sub n. Now, b sub n is the sequence without this negative in here. So it's this sequence. And that limit has to go to what? What do you think? 0. So you always check this first. Always check to see if the sequence is going to 0. Because if it's not 0, you're done. And then the last thing is, and they're not going to trick you. B sub n plus 1 must be smaller than b sub n. In other words, the sequence is getting smaller. So this one will converge because it's alternating in sign. The limit of 1 over n goes to 0, and it's getting smaller. 1/5 is smaller than 1/4. I can't make it any simpler. You're looking for alternating signs, and the limit of the sequence itself has to be 0. But that's no different than our very first one over here. So if it's not 0, you're done. Divergence. It's got to go to 0. So when I look at this one, let's see if we can write it with an n. Now, you don't have to be able to do that on the exam. They'll give it to you. It's -1 to the n. And then how do you write the k? Yeah. Loaded, your question? I can hear you. Yes. Okay. Yes. Yes. All this does is alternate the sign. It's positive, negative, positive, negative, positive, negative. That's all it does. And this is going to do the same thing. But what about the limit of this? Is that going to 0? So right away, I know I'm done. It's divergent. It's also not getting smaller. It's hard to say because it's alternating in sign. No, the first one converges because it's alternating in sign. 1 over n is getting smaller. Getting smaller this way. And the limit of 1 over n goes to 0. That's what the alternating series test says. It's the alternating harmonic series. It's convergent because of the alternating series test. It turns out that the alternating harmonic series is convergent. So that's what it says mathematically. Now, this b sub n is just the sequence without the signs in there. This means it's decreasing. This means it's alternating in sign. All it means. And the limit of the positive sequence, just like we've done before, has to be 0. It's not a divergence. So this is no different. And they're not going to trick you. They're not going to give you a sequence that is not decreasing whose limit is 0. I have a hard time coming up with one. Can't do that. Generally speaking, if you see an alternating sign, if the limit is 0, it's going to be convergent. That's just what's going to happen. And you're going to say, by the alternating series. So trying to ignore all the other writing there they have, because all you have to look for. It has to alternate sign. You look at the limit next, and then you look to see if it's sequence for all. Well, I don't know what number. This is alternating. It has to be decreasing, but it doesn't matter, because what we have to do is look at this first. This is easier to take that limit. Yeah, this is 3n over 4n minus 1. That's 3/4. That's all. It's not convergent because the limit is not 0. It's divergent. And you say, by the alternating series. So it's easy. Not that I know of, but that doesn't mean it doesn't exist. Yes. Okay, what about this one? It's alternating, right? What's the limit? It then goes to infinity of n squared over n squared plus 1. So it goes like 1 over n, so it's going to what? 0. Is it getting smaller? They're not going to make you prove it, but this term, n plus 1 squared over n plus 1 cubed plus 1, is that less than this? All you have to do is just write out the terms and see if you think it's getting smaller. So the first one's 1 over 1 plus 1. The second one's going to be 4 over 8 plus 1. The next one's going to be 9 over 27 plus 1. Is that decreasing? Yeah, clearly it's decreasing. Therefore, this converges by the alternating series test. I'm not sure what you're asking. Okay, Logan, what did you say? That just means it's decreasing. Proving that, you'd have to square all that out and cube it out if you really wanted to do it. But they're not going to ask you to do that. You're going to do it by inspection and just say, oh, I can see it's decreasing. Yeah, they're not going to, that's reserved for upper level. Now, you do not have to know, there's two kinds of errors that you're going to run into. There's the alternating series error. It only works for the alternating series test. It's the only one you have to know about. And then there's one for Taylor polynomials. And when we do Taylor polynomials, I'm going to wait and teach that error term right before the exam because you won't remember it. There's an error. Because when I add this up, negative 1 to the n, 1 over n, if I only add up the first 5 terms, that's not what that's exactly equal to. I have to add them all up, don't I? Okay, but let's look at what happens here. Now, forget all of this if you don't want to read it. You do not have to know any stuff about the remainder. But what it is all you're going to have to do on the alternating series, you guys, is exactly like what this kind of question asks. Find the sum to correct the 3 decimal places. This is what I call a brute force method procedure. You're just playing through the problem. Get your calculator out, because when these numbers are going to get small, and when these numbers get small enough that the first 3 decimal places are all zeros, then you've gone far enough. That's all. So it's negative 1 to the 0, and then it's 1 over 0 factorial. Now, it's a definition that 0 factorial is 1, because the mathematicians needed a 1 there. So they chose it that way. They could have made it 10 if they'd like. 0 would have caused a problem. They'd have to start with 1. They like to start with 0 some of the time. You can start with negative numbers too. Well, it's negative 1 to the first power, and it's 1 over 1 factorial. Plus, it's negative 1 squared. I'll write it out. Then it's 1 over 2 factorial. What's the sign going to be next? I'm lazy. I don't want to write out. 1 over 3 factorial. Plus, Logan, do you need to sit someplace else? Good. 1 over 4 factorial minus, what's the next one, Logan? 1 over 5 factorial minus 1 over 6 factorial. Whoops. Why is that? Because I'm being distracted. This is negative 1 to 0 is 1. Then this is minus 1 plus a half minus a sixth plus. Now, this one is 4 times. Because we have to do it. What are we missing? 1, 2, 3, 4, 5, 6, 7. Seems like they're all there to me. Aaron. All I'm doing is writing out the terms. Because what's 3 factorial? 3 factorial equals 3 times 2 times 1. So 4 factorial is 4 times 3 times 2 times 1. Or 4 times 6. So it's 1 over 24 minus, it has to go to 0 or it doesn't converge, right? 24 times 5? No. 5 times 4 is 20. 5 times 2 is 10, carry the 2. Okay, how about 1 6? 6 times 12 is 720. You're going to use a calculator. And then 7 times that? You have to. It says find it to correct the 3 decimal places. Okay. It says find the sum of the series of 3 decimal places. Is that going to go forever? Geometric ones go forever. Does this go forever? Is it geometric? 5040. Continue with this. You have to get your calculator out because all I have to do is divide this. So this goes. This is 0.5. I don't know what minus 6 is. Plus 1 over 24. What's 120? 1/20th is 0.05. You gotta have a calculator. No, don't do that. Okay, that's okay. So I want 1 divided by 120. 0.0883. And then I'm going to need 1 divided by 720, right? It's not small enough because this 8 is going to affect the third decimal place. That 1 is going to affect the third decimal place. It's not that hard. You keep going until you find one of these fractions. 1 divided by, and now you know you can do factorials out of this if you want. I can do 7 math under probability. Well, I gotta write that down. What is it? It's 0.001984. And this will not affect the first 3 decimals. Well, I think it will because there could be a carry here. But for the most part. So the first discarded term, that was 7 factorial, it would be 1 over 8 factorial. If you do 1 over 8 factorial, it's pretty small. It's still 3 zeros, maybe 4 zeros. And what's interesting about the error, all the error that's left, because if you add all this up, you can add it all up. This isn't going to change the first 3 places, and the next term isn't going to change the first 3 places anymore because it's getting smaller, right? You're getting more zeros. Alex doesn't believe me. I can take my calculator out because it said to find it. It said right there, find it correct to 3 decimal places. So we have to do this. Let's just go ahead and do it. So 3 decimal places. I want my number to be correct to 3 decimal places. So it's 0.5 minus the 6. So it's 0.5 minus 1 divided by 6. And then it's plus 1 divided by 24. We'll do that, 0.375. And then we did the minus 120. So we're going to do minus, pardon? What? Order of operations, it does division before it does addition. Answer, it's 1 divided by 120. I'm too lazy to write down all the zeros. Okay, so it's still changing in this third decimal place, right? And now I'm going to add in plus 1 divided by 720. As these get smaller, they're not going to affect that third decimal place. And then it's minus 1, I didn't miss anything yet, did I? 5040. 0.367, and then it's going to be plus, and then it's 1 divided by 8 factorial, right? Keep going until the third decimal place doesn't change, that's all. Math, that's why I thought we should do the problem. Whoops, I forgot the 8, but that's okay. I can do second, insert, 8. There we go. There, didn't change. Yeah, it's 0.36, because even when you do minus 1 over 9 to the factorial, it's only going to affect the outer places. It's only going to affect stuff out here. Nothing in here, so it stays. So this is the only one that works this way. You can't do this with the other one. The alternating series is the only one that you can do that. So you just, there's 3 decimal places, just you writing it out so it doesn't change. There's no thinking involved. The only other thing that I can say is, this is approximately what it's equal to. There's some more stuff here, and it's a plus whatever we call the remainder. And this remainder is smaller than the first discarded term. So we kept the factorial. So the remainder here will be less than or equal to 1 over 8 factorial. It will be no bigger than that. No, it's not, is it? It's good 4 places, actually. But you have A here too, so it would round up anyway. So still correct. And so they're gonna ask you this question, and the remainder is smaller than the first one, you don't count because all the rest of them will not affect the 0.367. So if you try to build something or use this as a model, this is good for 7 places. Now that's a factorial. N equals 7. Factorials go to 0 really fast, not fast enough really. I'd like to have it converge faster than that, but no, it doesn't matter because all they do is truncate. It says find the sum of the series for the first 3 decimal places. You can either go 0.368 or you can go 0.367. They don't care on the exam. It's not about rounding. It's about being able to do the problem. Yes, it'll be a multiple choice, but it's no harder than what this was. All you do is write it out. Not hard. So don't make it hard. You'll have some practice with it. There's a whole bunch of stuff on the error term in H3 that I skipped because I'm doing any of that error stuff. Okay, 2 last ones. Now this is kind of a minor theorem, but it's kind of important to get the order right on this. And this is absolute convergence. That was just the error for the alternating series. It's the only one you have to know is the error for alternating series, but it's not hard. I'll give you some practice problems. Okay. Now, I can say that this is absolutely convergence, my series, if I can take the absolute value of the sequence and have that converge. So here's an example. I have this series, which is alternating in sign. Does it converge? Absolutely. It converges absolutely if I do this. If I take the absolute value of this -1 to the n minus 1 over n squared. And what does the absolute value do to this problem? Makes everything positive. So it's like not having this here. Does this converge? Yes, because of the P series. Okay? It's as hard as it gets, not that hard. So since the absolute value of this converges, you would say that this is absolutely convergent. So if this converges, then the one with the alternating sign converges. This is how you deal with series that have positive and negative signs. So they don't have to alternate. The alternating series test works for the alternating ones, but what if it's not alternating, but you still get negatives? You have to do this. But the problem with it is the reverse does not hold true. Let's look at this alternating harmonic series. Is that, I didn't write much. Careful. What about this one? We know that this one converges. Why do we know that? Because it's the alternating harmonic series and we know it converges. So when you run into the alternating harmonic series on the test, you say it converges because it's the alternating harmonic series. You don't have to do anything. Everybody knows it converges. Yes. On my test and on the AP exam, you have to say why. Multiple choice on the AP exam, no, you don't have to. But if it's multiple choice in my class, yes, I want to know why. Because my job is to make sure that I know that you know the material so that you get it right with the test, right? Okay, is this absolutely convergent? If I do this, then this is going to get rid of the -1 and it's this one. Yes? Does this converge? I'm trying to get there. Does this converge? This is the harmonic series. So this is not absolutely convergent. It's nice if they're telling you it's absolutely convergent, that means you can ignore the negative sign. Here I can't. It's not absolutely convergent. This does converge, but its absolute value does not. That diverges, right. Can't forget that one, it's a harmonic. The most important one of all. Because this is harmonic. This is when does this converge? When t is greater than 1. And the integral is just the same thing. This is t is greater than 1. Okay, if a series is absolutely convergent, then the original series must also be convergent. But if the original series is convergent, that doesn't mean its absolute value is. So even though this converges, its absolute value does not. It's not going to bother you too much. I need it for the last and the best test of them all, the ratio test. Well, you guys like the ratio test, even though there's a lot more work to it. Let's look at this one. Let's write out some terms. This is the cosine of 1 over 1 squared, plus the cosine of 2 over 2 squared, plus the cosine of 3 over 3 squared, plus the cosine of 4 over 4 squared. Okay, guys, question? I'm just writing out some of the terms, right? And you remember that all students take calc. So, now that's a radian. Guys, it's not a degree, it's a radian. How big is a radian? Anybody? It's approximately 60 degrees. It's really 57, but they just have, but it's close enough, 60 degrees. So in the cosine of 1 is going to be over here in this quadrant. Cosine of 2 is 120 degrees. So it's going to be over here. So this is going to be negative. What about the cosine of 3? It's going to be just about there. It's going to be negative. Cosine of 4 is negative, and then we're probably going to get to some positives. Because I know that the cosine is negative here and the cosine is positive there. It's just like 4 times 60 degrees, 240 degrees. 1 radian is about 60 degrees. So 2 radians would be about 120. Less, a little less. 3 radians is going to be less than pi, less than 100 degrees. Makes a what? Won't make any difference. The point is that this is not alternating, so I can't use the alternating series there, which is unfortunate. But I can use the absolute convergence test, because the absolute convergence test says that if I take the absolute value of this, if that converges, then that has to converge. Now that might bother you, why does this converge? I'm going to use the comparison test. Now the cosine of n, the absolute value of the cosine of n, will be a positive number. How does that compare to 1? Less than or equal to 1. Now can't I divide both sides by n squared? Now let's use the comparison test. This we know what? Converges, right? By the p series. Well, if this is smaller, if this is smaller than that, this must also converge by the comparison test. Because there was a test that said that if this series is smaller than this one and this one converges, it's trapped above and below. That's got to converge too. Doesn't that make sense? If you take this and you make your other series smaller than that, and that converges, what has to be true about that? Because I've had the experience and I've done the homework several times over, which is the point. No. Sometimes I do, but these, they all look so different all the time that no. Okay. Just going to wait. After class, we got to get through this. Now, because the absolute value of this converges, what do you think about the original one? It converges. That's the theorem that says it's absolutely convergent. So if you get negatives, you want to try an absolute value and see if you can get the absolute value to converge. And all you do on the ratio test is you ratio the n plus 1 term to the nth term. Where do I use the ratio test? When I'm doing n factorials and n to the n. That type of thing. When I'm looking at things that are discrete and not continuous. Yeah, I'm going to give them to you all mixed up. I have a worksheet that I have to get off for you, and you're going to figure out which way to do it. And there's more than one way to do some of these problems. But the factorials can only be done with the ratio test. And now these are going to be absolutely convergent, which means if you have negative signs in there, we can ignore them because the original series will also be convergent. If the ratio turns out to be a number less than 1, it converges. If you focus, it's a lot easier. And if the ratio turns out to be bigger than 1, it diverges. And if it's equal to 1, we know nothing, unfortunately. So, I would never do the ratio test on these problems. We're going to do one of them, and you could do both of them if you want. But let's do the ratio test on the summation of 1 over n squared. Now, when you do this on the exam, they're looking to see you use the ratio test. They're in particular looking for that. So you might even say ratio test. You can. I'm just going to show you how you do the ratio test. And here's the problem with this one. It's the limit of the absolute value of a sub n plus 1 over a sub n. Like I said, you do this with the factorials. For these powers, no, I use the p-series. You're right. I mean, I know that this one, I understand that. I'm showing you how to use the ratio test. And what happens to the ratio test in this situation? Now what I'm going to do is I'm going to get rid of absolute value. As long as you put it somewhere in the problem, I would not omit it entirely. Yes, those are positive, but they're going to want to make sure you know it's absolute value. Just because they get picky about that. But I'm going to get rid of it for positive terms. So you put in n plus 1 for n, and then we're going to do a real problem. And you're going to divide it by 1 over n squared. Well, what's going to happen here? We're going to multiply by n squared, multiply by n squared. In fact, I'm going to do it a little differently than I did in my other class. So it's the limit. Well, I squared that out, but I think it'd be nicer than that. And I get n squared over n plus 1 squared. That goes away. Well, I don't know if you realize this, but I can rewrite this. It's the algebra that's going to get in our way right now. This is n over n plus 1 squared like that. That's the property of a squared over b squared is the same as a over b squared. So that's one of the properties that we're going to have to understand when we are looking at the ratio test. And now what's the limit of this inside thing? So it's 1 squared, so it's 1, so we know nothing. Huh? We already knew that, and if you don't do this one, I'm running out of time to do it, but if you do this one, you also find with the ratio test it's 1. No, it isn't. We still have to, not leave it until we're done. So let's look at how do you, exponentials, that's another one. See, I can't integrate that. And I can't compare it with with anything because I don't know what to compare it with. So the comparison test only works when you're looking at p-series. Because that's the only thing I know about. I don't know about this. So we're going to do the ratio test, and it's the limit as n goes to infinity, and I want you to try some of these problems. I do know you have a concert tonight. So it's negative 1 to the n plus 1. What? No, there's something one. Okay. Now, that's going to be divided by this thing. Oh, it's not that bad. Once I show you how to do this, you're going to say it's not that bad. Hey, guys, if I divide by this, can't I, well, let's go ahead and divide by it. It's negative 1 to the n is n cubed over 3 to the n. Now, do I have to worry about the negative ones? No. So let's make this nicer. N going to infinity. It's not that bad. It's n plus 1 cubed divided by 3 to the n plus 1. And dividing by this is the same as multiplying by its reciprocal. It's okay, if you write out the original a sub n plus 1 thing, it's okay to jump right to this. That's okay too. Now, to make my life a little easier, I'm going to switch the denominators, because that's just a times b equals b times a. Or, sorry, 3 times 3 is 6. Okay? So it's the limit as n goes to infinity, and they all work out in a similar way. You want to write it like this. N plus 1 cubed over the 1 it's like. It's like that one. And then you have 3 to the n over 3 to the n plus 1. Now I just have to reduce that, and that's not bad. Because what's the first factor to look like? I know, but I'm going to run out of time. This is n plus 1 over n to the third power. You're right, that's 1. And this is 3 to the n over 3 to the n times 3 to the first. That bother you? Because what do you do with the bases are the same? You add the exponents. N plus 1 to get n plus 1. So this is going to cancel. And this is, you said that's 1. And so this is 1 over 3. 1/3, which is less than 1, so it's inverted. Yeah, but when we skip the first step that I just did over here, and just go right to that, it's a lot easier. Then it's not so bad. But usually you like this, it's highly symbolic. So let's try the last one. No, we have 3 minutes. I think you're going to have some problems with it, so I think I better help you with it. Now we're going to get it done. 2:37. So let's get it set up. I'll let you think about it. Let's just get it set up at n plus 1 to the n plus 1 over n plus 1 factorial. So what are you going to do with that? And the n plus 1 to the n plus 1 might bother you as well, times, and then you're going to multiply by the reciprocal, n factorial over n to the n. So what is n plus 1 factorial? N plus 1 times n minus 1, 3, 2, 1. So it's n plus 1 times what's this? No, n factorial. That's what a factorial is. 5 factorials. 5 times 4 times 3 times 2 times 1. So n factorial is n times n minus 1, n minus 2 times 3 times 2 times 1. I'm trying to figure out what n plus 1 factorial is. It's n plus 1 times n factorial. What's n plus 1 to the n plus 1? What's the limit? Let me figure this out. N plus 1 to the what? N, right? Times n plus 1. And let's go ahead and put the n to the n down over here. Let's switch these. Then I get n factorial over n plus 1. N factorial. Yes. I challenge you to figure out what that limit is. It's not as simple as you think. Okay? You guys try it.